Welcome. In this section, what we're going to be doing is trying to get a handle on why are materials the way that they are. And in order to understand this, we need to understand more about those building blocks that are used to make up the entire world around us. So we need to understand a little bit more about how the elements work. You see, the elements are arranged on the periodic table, and the periodic table holds a ton of information on it. And the periodic table may look kind of strange in the way that it's put together, but it's all based on one rule. You see, the periodic table is based on what's called periodic law. It states that when elements are arranged in order of their increasing atomic number, their physical and chemical properties show a periodic pattern. So, what does this actually mean? Well, periodic law means that elements end up repeating their behavior. So, if you were to arrange the elements in a big line, what you would see is they behave a certain way. So, each one does its own specific thing. And then you're going to get to a point where they start repeating what a previous element was doing. And then the next element will repeat what another element did. And you see repeated periodic behavior. And this happens multiple times. On the periodic table, we actually see this in the way that it's laid out. You see, on the periodic table, it's arranged into two separate parts. It's arranged into what are called the periods. Periods represent the rows. So there are 7 periods on the periodic table. The first period only contains hydrogen and helium. The second period has lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and then so on. Third period, fourth period, fifth period. But there are also what are called the groups or the families. So in the first column, this is what we would consider to be the first family. On the periodic table, elements within a family show the same behavior. So that means hydrogen, lithium, sodium, potassium, rubidium all kind of do similar things. Same with the other end of the periodic table, helium, neon, argon, krypton. They all do the same things, and that's because they are in the same vertical column or the same family. The periods, on the other hand, they represent different the elements that are actually doing different things, but every time you jump down a period, you see repeated behavior start over. Now, we should probably ask why. When the periodic table was initially made, it was made in 1869, and the person who made it, Dmitri Mendeleev, didn't actually know anything about the structure of atoms. He didn't know about protons, neutrons, or electrons, but what he created is actually based off of the structure of the atom. You see, all of this behavior and the way that things work comes down to structure. And that's because structure determines function. The way things are put together determines the way that they work. And in order to demonstrate this, let's take a look at some simplified atoms. So we're going to take a look at what's called the Bohr model of 3 atoms, all in the same family. So we're going to start by taking a look at the atom hydrogen, literally the simplest atom. Now, to draw the Bohr model, you need to know the protons, the neutrons, and the electrons. And the protons for hydrogen is the atomic number, which is 1. The neutrons for hydrogen is the atomic mass of 1 minus the number of protons. So hydrogen has 0 neutrons. And the number of electrons for a pure element is the same as the number of protons. So it has 1 electron. Now, I just want to make sure I have lots of room to work here. So I'm just going to lose the work and I'm just going to write 0 neutrons. So let's draw my atom of hydrogen. So it's going to have 1 proton, 0 neutrons in the nucleus. I guess I didn't even need to write neutrons. And then remember in the Bohr model, the first ring can hold 2 electrons. We only need it to hold 1. So I'm just going to write my electron on that line. Next thing I'm going to do is draw the next atom in the same family. So I want to draw lithium. next. And so we need to know protons, neutrons, and electrons. Lithium has 3 protons, so same number of electrons. And it has an atomic mass around 7. Minus 3 gives us 4 neutrons. So in the nucleus, we have the protons, we have the neutrons, and then our first orbital can hold a maximum of 2 electrons. Once that orbital is full, we need to add a second orbital. Remember, this orbital could hold a maximum of 8, but we only needed to hold 1 because we only need 3 electrons. And then we're going to go to the next element in the same family. And so that's going to be sodium. Sodium has 11 protons, 11 electrons, and 12 neutrons. Now I'm just going to switch to a smaller, finer marker for this. What we're going to see is we have our nucleus, so 11 protons, 12 neutrons, surrounded in the nucleus. First orbital, 2 electrons. Now, the second orbital can hold a maximum of 8. So once our first orbital is full, we're going to fill our second orbital. So 4, 5, 6, 7, and 8. That gives us 10 that we've used, and we need 11. So that means we need one more orbital. And that one orbital is going to have 1 electron in it. Now, when it comes to the behavior of atoms, it's important to understand what actually causes the behavior. See, protons just determine what the element is, but what determines the way it behaves is the electron. And so what we want to look at is the electrons for each of these elements. And hopefully one thing that you notice as you look at this is that in the outside orbital of every single element, there is only 1 electron. And you see, this is what we would refer to as valence electrons. So a valence electron is an electron in the outermost orbital. And so this has, our hydrogen has 1 valence electron. Lithium has 1 valence electron, right? It was this one. In hydrogen, it's this one. In lithium, and sodium also has 1 valence electron, and it's this one. This is what determines the behavior of this set of elements and makes them end up doing pretty much the same sort of things. They have the same physical properties, so the same properties when they're not going through a chemical reaction, and very similar chemical properties, the properties that you get when something does go through a chemical reaction. And so you end up seeing this behavior all based off of the valence electrons. And because they have the same number of valence electrons, they show the same behavior. Now on the periodic table, this emerges in the family. You see hydrogen, lithium, and sodium are all in the same family because they have the same amount of valence electrons. This would be true if we went to the next family. If we were to look at family number 2 with beryllium, magnesium, calcium, you would end up seeing that they have 2 valence electrons. And because they have 2 valence electrons, they're going to behave in a very similar way. Column 13 has 3 valence electrons, so they behave in a very similar way. You see, the structure of the atom is really what's determining the behavior, which is why we have the structure of the periodic table. There's another thing that we can take a look at in this structure as well. You see, hydrogen is in period number 1. So period 1. Lithium is in period 2. And sodium is in period 3. Hopefully one thing you also notice is that the valence electrons for hydrogen are in the first ring, the first energy level. The valence electrons for lithium are in the second orbital, or the second valence shell, the second energy level. The valence electrons for sodium are in the third energy level, or the third valence shell. You see, on the periodic table, the actual energy level, or the distance from the nucleus, or the ring that the electrons are going in, is what determines what period something will actually be in. If we take a look at our periodic table, hydrogen is in row or period number 1. So its valence electrons are filling the first energy level. Lithium is in row number 2. And so its valence electrons are filling the second energy level. Sodium is in energy level number 3, or filling its valence shells into the third orbital, so it fits into period 3. So you see, a lot about the structure of the atom is fit into the periodic table itself, and this is what led Dmitri Mendeleev, the constructor of our modern periodic table, to make it the way that he did. And what was so fascinating about him is that he actually predicted elements. So he discovered the pattern behind the elements and knew it so well that in 1869 he knew they would discover more elements in the future. To give you an example of this, he predicted an element called Eka manganese. You see, Eka means beside or below, and so he thought there would be an element discovered below where manganese should be, and it eventually was. You see, it was discovered in 1939, and so that's about 60 years after he initially made the periodic table. They didn't discover that element until after he died, but they were able to, or he was able to make that prediction because he knew periodic law. And periodic law is why we see so many trends emerge on the periodic table and so many patterns in the behavior of the elements. And so hopefully this helps you get an understanding of why elements are the way that they are, why the periodic table is set up the way that it is, because atoms are really the foundation of chemistry. And as we start to understand why the world and universe is constructed the way that it is in the material sense, in matter, then we need to understand the way that the atoms actually work so we can figure that out. So hopefully this gives you a good foundation, and I'll see you next time.